Okay, so topic of today's video will be matrices or a matrix. A matrix is this thing right here. A matrix is an array of numbers. We say matrices if we have more than one, but just as it is like that deal right there, that's called a matrix. And it's just like I said, that's an array of numbers. It has columns and rows, and there's some jargon about it that I'm going to tell you about. But before we do that, let's talk about this example I'm going to do here in a little while about, well, why would we put numbers in an organization like that? Okay? And part of the answer to that is that it might be how we want to organize some information. So here's a problem I'll do later, has some information organized in a matrix. Students in a class with their grades on a midterm and a final, okay? And then I have some purpose that I want to accomplish by putting the information in a matrix like that. But if it's just information, if that's how you need to organize it, you can do it like that. And that's what this is. Now, it doesn't say what the 2 is supposed to be or what the 15 is or so on, but in any case, that's what a matrix is. Now, we have here 3 columns. The columns go vertically, and we have 2 rows. And so we say the size of the matrix is 2 by 3. And that's always the rows, and that's an X. It doesn't mean I'm multiplying. It says 2 by 3 columns, and that's what you're looking at, 2 rows, 3 columns. So we might be given a matrix, and then we'll say its size sometimes, and then we might say something like this. Okay, here's how you read this. A subscript 1, 3. Okay, and the A is just a variable or an unknown. We're looking for a specific number, and that number is the entry in row 1 and column 3. So you look at this thing and you say, there's row 1, there's column 3, and what's the number that's in row 1 and column 3? It's a 4. Okay? So we have a matrix, it has a certain size, and if we're interested in a particular number in it, we might call forth that number like this. Okay? All right, now none of that's hard, you just have to get used to how it's done. The only thing I think that's hard about matrices is to multiply them. And so here's an example where I give you a matrix capital A and matrix capital B. And I say, can you multiply them? All right. Okay, so A times B, what I did to get started on it was I wrote down A first and then B second, just like it says. And the procedure goes like this. I multiply the rows of the first one by the columns of the second one. And I do that in a very specific way that I've outlined here. Okay, now this is our first example. We'll do another one. We'll get used to it, but it says, we'll do like this. Row 1 times column 1. Row 1 times column 2. Row 2 times column 1. Row 2 times column 2. See the pattern? R1, R1, R2, R2, C1, C2, C1, C2. That's how we would multiply the rows of the first one by the columns of the second one. All right, now here's what that looks like. When I say in this entry right here, multiply row 1 times column 1, then here's row 1, here's column 1. And the way that we imagine doing that is we take this column, we pick it up and like turn it sideways so it fits right on top of that one. So you got to use your imagination a little bit. If I take this column and I pick it up and put it here, I get a 5 on top of the 9 and a negative 5 on top of the 3. Okay, so we'll multiply those together. We'll get 45 and 15. We add the results together, we get 60. So 60 is this entry that should go right here. Okay, now let's try to do the others more or less from scratch. Here, row 1 times column 2. So there's row 1. And then this would be column 2. Again, imagine if I pick this up, turn it sideways like that, how would it fit over this row. The negative 2 would be on top of the 9, and the 5 on the 3, see? And then we multiply together, we get 18 right there, and we get negative 15. Right, and then I just combine these results, so that's going to be a 3. Okay? All right, so we get 3 right here. So 60, and then 3. All right, and then we keep going. R2C1. Okay, so that would mean row 2 times column 1. Okay, so imagine that we have row 2 right there, 8 and negative 4. And then we multiply that times column 1. And how do I mean that we multiply it by column 1? We take this, we turn it sideways, we put it right there. So that's going to be a negative 5 will be on top of the 8, and a negative 5 on the 4. Then we multiply those numbers as they would lay on top of each other as I turn it like this. And that's going to be, I'll get negative 40, and then plus 20. So I'll get negative 20. Okay. Negative 20 goes here. All right, now so all it is a pattern. All it is a pattern that you would have to learn. I'll give you the last one. There would be the instructions anyway. It's not really much different than how I did the first 3. But the last one's going to be negative 36. Okay, so see if you could come up with that. All right, so there's matrix A times matrix B. That's our first example to look at about how you would multiply matrices together. Now, before we do the next one, let's look at something. In general, this is how it's going to work. If I multiply A times B, they're both 2 rows, 2 columns. So we would say it's a 2 by 2 times a 2 by 2. There's something that's always going to have to be true about this. When you write them together, as they're given, these interior numbers must match. And then the size of the answer will be this by this. So, if we didn't even do it, we'd say, well, those match, so the multiplication can be done. If they don't match, the multiplication can't be done. And we get a 2 by 2 as a result. So yeah, I got a 2 by 2. Okay? All right. Now let's do one from scratch then. B times A. Now we did A times B, so B times A. Here's what B times A is going to look like. B is negative 5, negative 2, negative 5, and 5, okay. And then A, negative 9, negative 3, 8, negative 4. Okay? Now, when we do this, that answer is built just like this. Row 1, column 1, row 1 times column 2, so on and so forth. So it's made exactly the same way. All right? So how about this? How about I'll find that last number right there. And then I'll tell you what the others are, and you see if you can work them out. I mean, if you can do one and you see how the pattern is supposed to be established, you can do them all. So how would I find, I'm going to get a number here, 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 there. I'm going to get a 2 by 2 matrix as an answer. How do I get this last one? Row 2 times column 2. So let's write that out. What would row 2? So row 2 is here. Okay? And then column 2 is here. Because it's always the rows of the first one times the columns of the second one. Now, how though? Row 2 is negative 5 and 5. How we multiply that row by this column is to take this, turn it like that, and see how it fits on top of this one. The negative 3 will be going right on top of the negative 5, and the negative 4 will go on top of the 5. Okay, and then we multiply according to how they would fit onto each other, and we combine our results. So we're going to get 15 right here. Then we're going to get negative 20, so that's going to be negative 5. Okay? So that result should be negative 5 right there. Now we would find the others in the same way as I gave up there. Here's what you're going to get though. 29, 23, and then 95. I'm sorry, 85. Right there. Okay. And that will be our answer. Alright, now, as tedious as that might be, you kind of get the feeling that, okay, I can do this. If every time you multiply a 2 by 2 times another 2 by 2, if that's what it looks like, then I know how to do it. Alright? Now, let's look at a different example. Just, because you won't just see one like that. You might see that you have matrices of some other size, like what we have right here. Okay? Alright, I got matrix A, which is what? A 1 row, 4 column, times matrix B, which is 4 rows and 1 column. Okay? Now, that other example, what do we say had to be true in order to multiply two matrices together? We said that these have to match, and they do. Okay? 4 and 4 is the same. And so what are we going to get for an answer? We're going to get a 1 by 1. So we're going to get a matrix that's 1 row and 1 column. Alright? Alright, now so what would that be? Think about it right here. It's always like this. R1, C1, R1, C2. What if there was another one? R1, C3, R1, C4, R2, C1, R2, C2. What if there was another one? R2, C3, R2, and then what? R3. You can keep counting just like this over as much as you need to. Now, so given that the answer is 1 by 1, all that I could possibly do is multiply R1, row 1 of the first one, times C1, column 1 of the second one. That's all there is. Okay? Alright, because what do? The rows of the first one times the columns of the second one. Okay? Alright, so this will have only one entry in it. The answer is a 1 by 1 matrix. So let's see. Imagine, how do we multiply the row right there times the column right there? We take this, we pick it up, we turn it sideways just like this, and we see how the numbers fit on top of each other. So let's do like I did before. R1 is 3, 4, 5, 6. C1 right there. If I take it and turn it like that, it's going to be 3, 4, 5, 6. Okay, so we'll get 9 plus 16 plus 25 plus 36. Okay? And so we add all that together, we get 86. Okay, so answer. A 1 by 1 matrix with just the number 86 in it. Okay, so that's how we do A times B. Now, as you saw in the last problem, I can take two matrices, multiply them one way, get an answer, and multiplying them in the opposite order gives me something different. Okay? Alright, so I have, for the sake of comparison and for us to learn the pattern, B times A. Okay, so let's see. I guess as we do this, and if the problems look different, one thing that we can count on is it's always going to work like that. So B times A, what do you have there? B is, let's see, it's rows by columns. It's 4 by 1. B is 4 rows, 1 column. 1, 2, 3, 4 rows, 1 column. And then A is 1 row, 4 columns. Okay? And those interior numbers match. And so the answer is going to be a 4 by 4. Okay. All right. Now, remember this pattern I gave you right here? I said that's always how it's going to be. Make the rows of the first one times the columns of the second one in specifically this way. Can you fill this out so that it makes a 4 by 4? Let's see, it was the pattern R1, C1, R1, C2. Okay, so I get it. R1, C1, R1, C2. Now we got a 4 by 4 matrix for an answer, so I guess R1, C3, R1, C4. Okay. And what about the next one? Let's see, what was it? R2, C1, R2, oh, so you get the idea. R2, C1, R2, C2, R2, C3, R2, C4. Okay? So you get the idea. All right, I'm going to trust that you see. All right, that's how it goes. I'm going to just put the dots. So you fill that in. R3, C1, R3, C2, R3, C3, R4, C1, R4, C2 to make a 4-row, 4-column matrix. Okay? All right, now let's have a look at this. How about I've got my instructions. One thing I didn't do was I didn't write them together. So let's see. I'm going to take B. Here's B. 3, 4, 5, 6. Times A. 3, 4, 5, 6. Okay. So we're supposed to take the rows of this one times the columns of this one, right? And we'll start off, we'll do row 1 times column 1. Now, what is row 1 of this matrix? Right there. It just has one number in it. And what's column 1 of this one? Right there. Okay, so, I mean, I know on the others I would say something like, imagine that you pick this column up and you turn it sideways like that. You know, how would the numbers, they would fit over each other like this. And we multiply and combine our results. Anyway, so, well, here there's nothing to turn. I mean, it's just a 3. So aren't we just going to get 9 right there? Yeah. And then what about row 1, column 2? Well, here's row 1, here's column 2. It's going to be 12. And then row 1, column 3. Well, here's row 1, there's column 3, 15. Okay? And then row 1, column 4. There's row 1, column 4 is here, 18. Okay? All right. Now, so you get the idea. You go to row 2 times column 1, 2, 3, and so on. And what you can do is pause the video, see if you can do all the math, and unpause it. I'm going to fill in the answer. Because really, I don't think the math is hard. It's the pattern that you have to get used to. So you get here 12, 16, 20, 24, and 15, 20, 25, and 30, and then 18, 24, 30, 36. Okay, and there will be our answer. We said that you would get a 4 by 4 matrix as an answer. 4 rows, 4 columns, just like we're supposed to. Okay, now, so I could anticipate the question of, why in the world would we multiply matrices like this? What would the point be, and so on and so forth. Okay, so time to address that. I told you that a matrix just gives us a way to organize information. So, I could do something like this, all right, if I wanted to. I could organize the students' grades for a class like this. And imagine this scenario. Here's the scenario. So here I've got that there's a class and there's just 2 grades. There's a midterm and there's a final. And let's say there's 5 students in the class. You can interpret it that student 1 got a 76 on the midterm and a 92 on the final. All right? Now, there's two, let's just hypothetically, let's say there's two different grading systems that I'm considering. Or maybe like I want to give students the benefit of the doubt, or giving them an option to get the best grade. And I'll say, I'll either grade you on System 1 or System 2. Okay? So here's my students, and here's their grades. And then here's the two grading systems that I'm considering. And here's how you could interpret it. That on System 1, the midterm and the final are both 50%. And System 2, the midterm's 30%, but the final's weighted more heavily, 70%. Okay? All right, now here's what I could do. If I multiply A, this matrix, times B, this one, it'd give me a way to calculate the grades in just one procedure. I could see how each student would do under each grading system. And then maybe I would just give them the higher grade as a result. Okay? All right, so here goes. Let's do this. Let's multiply A times B. Here's matrix A, here's matrix B, and we'll interpret all the numbers that we see. Okay? All right, so A times B is going to be, all right, 76, 92, 74, 84, 94, 86, 84, 62, 58, and 80. Okay, so that times this. And I just rewrote them because I think if we're going to do this, it's nice to see them together. Oops. Okay, so there they are. You're looking at them right next to each other, just like we should. Now, it's not always possible to multiply two matrices. Remember what I said? If you were to write down their sizes in the order that you're multiplying them, these interior numbers have to match, and then your answer is going to be as big as this by this. So we should make sure of that. What do you have here? 5 rows, 2 columns, times, how big is this one? 2 rows, 2 columns. Those match on the inside, so that's good. So we're going to get a 5 by 2 as our answer. We're going to get an answer that's 5 rows and 2 columns. Okay. Now, what I would like to do is see if you could remember this whole pattern right here. Row 1, column 1, row 1, column 2, row 1, column 3 if you need to. Row 2, column 1. You know, you keep going. So, all right, I got a 5 row, 2 column. And it's going to look like this. R1, C1, R1, C2. It's got 2 columns. I'm getting a 5 by 2. 5 rows, 2 columns. There's first row. R2, C1, R2, C2. R3, C1, R3, C2, R4, C1, R4, C2, and then the last one, R5, C1, R5, C2. Okay, so that's the pattern. Row 1, row 2, row 3, column 1, column 2. It really is no different than this very first one that I showed you. I just have to extend it a little bit to be the size that the answer needs to be. All right, now, so let's do this. I'm not going to, I told you, it's tedious to multiply matrices by hand, which is paper and pencil. I'll do a few of these so you can see that it looks the same, and then I'll just fill in the rest of the answer, okay? Let's do like this. Let's do like those two. What's row 1 times column 1? What's that even mean? It means first the row 1 of the first matrix times column 1 of the second one. Okay? Now, how again? Take like this. I'm going to put R1 here, 76 and 92. Column 1, You got to pick that up and imagine that you turn it sideways like this. I'll get a 0.5 on top of both of them. Okay. All right, now you would multiply 76 times 0.5, 92 times 0.5. You add your answer. So I'm just going to do like this, 76 times 0.5 plus 92 times 0.5, and I get 84. Okay, so that's going to be 84. So that means this number should be 84. And let's do this other one, R1 times C2. What's that mean? Row 1 of the first matrix times column 2 of the second one. Okay, so let's do scratch work over here. R1, C2. So R1 is 76 and 92. C2, if I pick it up and turn it sideways like this, I get a 0.3 like so, and then a 0.7. Okay? Alright, so 76 times 0.3 plus 92 times 0.7. So let's see, 76 times 0.3 plus 92 times 0.7. So I get 87.2. Alright. Now here's how we can look at it. Alright, if I go no further, this is, here's what this represents. Student 1, if graded under System 1, where the midterm and the final are both 50%, what's that? How would you do the grading? You'd say 0.5 times 76, that's 50% for the midterm, plus 0.5 times 92, that's 50% for the final. That would give 84. But under System 2, that same student, what would the grading be if the midterm was 30% and the final was 70%? We would say 0.3 times 76 plus 0.7 times 92. That's going to give you 87.2. So I could look at it like that the first student gets this grade under System 1 percentages and gets this grade under System 2. And like maybe I'm going to consider both of those and just give the higher grade. So they'd get an 87.2. All right. So that's student 1's final grade under either System 1 or System. That's how you can interpret those numbers. Anyway, so for the rest of it, let's do, since the math's the same, how about, let's just do like this last one. Okay, and then I'll tell you what I think that means. R5 times C2. Okay. R5 times C2. Imagine if I had row 5 times column 2. Now I've written the others down. Let's just do like this. Pick it up, turn it this way. That's going to be 0.3 times 58 plus 0.7 times 80. So there you're looking at it. 0.3 times 58, 0.7 times 80, and I'll get 73.4. Okay, so what's that mean? It means that student 5 under grading System 2 would get a 73.4. Okay. So I didn't do these 3 or these 4. So in red there, those are the ones I didn't do, but I've showed you the pattern, I showed you how to write it down, and that's the hard part. Once you have this in front of you, those are the instructions for what to do. And it's not like it's any different from there between one example versus another. Okay? All right. So that's, well, what have you seen here? How you multiply matrices just randomly. And then an example about me trying to organize some information, multiplying the matrices, and interpreting what the answers would have to mean. Okay? Alright, so you can think of this as like the real example for why we use matrices and what we could accomplish by multiplying them together. Alright, now, last thing I want to show you in the book or in the My Math Lab assignments, you'll see these problems about solving 2x2 system of equations with something called Cramer's rule. Everybody just pronounces it Cramer's rule, so that's what I'll call it. And this, I mean, if you looked at my other videos, that should not look like an unfamiliar problem. Okay? We could solve this by substituting the y or by adding the equations together and canceling the y. In other videos, I've talked about how to do it, but there's this rule that uses matrices. It's actually pretty easy to do, so everybody learns it. Okay. Here's how we do it. We do this with something called determinants, and the determinant allows us to solve it like right away. Like we don't really have to do any figuring out about what do you do with the x and the y. Okay. Now it's one of these things. It's like almost anything in math. It's just better if I show you rather than tell you. Here's what we do. Notice how this problem, it's like perfectly organized. I got the x's in one column, I got the y's in the next column, then I got an equal sign, then I've got just numbers. Okay? Here's what we do. Take the coefficients of the numbers that you see with x and y and put them all right here in exactly the same way they're given. So I've got like 1x, 1y, and then 1x and negative 1y. Okay? Now, if you're trying to solve for x, up here, in the first column, which represents x, we put 6 and 4. Now, in other words, how about this? Copy this down, but leave the first column blank. Why leave the first column blank? Well, because we're trying to solve for x. So just, copy that down, but we'll put 6 and 4. They're solving for x. Okay? All right. Now, so that's the setup. Now, I've written this down. I haven't told you what we do with this, but I have told you that that's how we get started. Now, these vertical lines tell me that I'm going to calculate something from that matrix called a determinant. Okay? And to do that, I told you it'd be just easier to show you than tell you, but how about this? Here's the formula, okay? Say I want the determinant of a 2x2 matrix just like those. Here's what you do. You multiply diagonally this way, a times d. You subtract whatever you get if you multiply diagonally this way, c times b. That's what you do. A times d, c times b. Subtract them, just like that, every time. So let's see. What's this going to be? 6 times negative 1 minus 4 times 1. There's exactly that formula. And about this one. 1 times negative 1 minus 1 times 1. I just copied that down for what you see here. Okay, so anyway, so what's that going to be? Negative 10, if you take negative 6 minus 4, and this is going to be negative 2, negative 1 minus 1, negative 2. So that's going to be 5. Okay. All right, so that just says that the x should be 5. Now, how should we write down our answer? I guess no matter how you solve it, the answer has the same format and meaning. And we'll say there, 5 for x. We haven't figured out the y. Now I know that if you know x is 5, I'm aware that you could put the 5 here and solve for the y, or you could put it there and solve. I realize that's not that hard to do, but the goal of me showing you this now is to show you Kramer's rule. So okay, suppose you're going to solve for y. Okay, how could we adapt this? Here's what we do. Take this bottom determinant is always what the coefficients of the x and y are in the order that you see them. So it's going to be this all over again. 1, 1, 1, negative 1. Okay. And then this top part, well, if I'm going to solve for y, it's the y column that gets replaced by the 6 and the 4. and this is otherwise the same. Okay, 1 and 1. All right, there it is. All that top one is it's going to be this one, but if you're solving for y, replace the second column, y is in the second spot, with these numbers, 6 and 4. Okay, that's what you do. I wrote that in red there, hoping that stands out. Anyway, so now how do you calculate the determinants? Well, that's like this. Multiply diagonally this way and that way, and then subtract. So I'm going to get a 1 times 4 minus a 1 times a 6. And then I'm going to get a 1 times a negative 1 minus a 1 times a 1. Okay, and that's going to be 4 minus 6, which is negative 2. And that's going to be negative 1 minus 1, which is also negative 2, which is 1. Okay, so 1. Should be that x is 5 and y is 1. Now, this, seems totally different than the problem that we're given, and that's not how we learned to solve the same problem before, but let's see, does it work? Is 5 plus 1 6? Yes. And is 5 minus 1 4? Yes. So it's obviously the answer. Okay? But if you see problems that say use determinants, that is called a determinant right here. Okay? And this method otherwise is called Cramer's rule. Okay, so you see problems that use terminology like that. The math is not hard. All you see right here is how you arrange everything and do the calculations.